So in your notes, that one of your classmates asked, "What are we doing? Like, what is this unit about?" So we are still in the light unit. We're still talking about light, but instead of like dissecting a light wave or understanding the different types of light waves, now we're talking about properties that are true for all light waves. We talked about Doppler effect. We talked about polarization. These two are two more of them. The first one is reflection, and then tomorrow we're going to talk about refraction. But let's focus where we're at right now, which is reflection, okay? Reflection is a property that happens, one of the two properties that happen when a wave encounters a new medium, okay? So let's write that down, reflection. One possible outcome, and by that I mean it's always going to happen a little bit both ways, but one possible outcome when a wave encounters a new medium. So we've talked about reflection a little bit, reflection a little bit before. We did this when we did our speed of sound lab. Do you remember that sound wave went down the tube? It reflected off the bottom and bounced back. When we talk about a sound wave, reflection is known as an echo, okay? When we're talking about a light wave, we talk about it literally as reflection. That's the reflection back that you get from looking at a mirror, for example, okay? So we're going to look at this kind of in two pieces. The law of reflection has two parts to it. Part one, you figured out in experiment one, and part two, you figured out in experiment two. So we're going to kind of go through them one at a time. So experiment one, what was your big conclusion that you came up with from experiment one? You can look back if you need to. Think back if you don't. Yeah, so we set up the mirror, right? So we're just going to kind of draw this so we remember. And then we put an object over here. And this is the physical thing, right? So I'm going to call this the object. That's the technical term we use. The object is the thing that gives off light. Now, the light it gives off happens to be reflecting from the lights around us, but it's the thing that's giving off the light that we're talking about. And then the other one that we put over on the other side of the mirror, that was what we call the image. So the image is light that converges or appears to converge at a point. The mirror that we used here is what we call a plane mirror or a flat mirror, okay? You have had lots of experience with plane mirrors in your life. Every time you brush your teeth, so twice a day, I hope, and your dentist hopes as well, you look at your face in the mirror, right? And you're looking at a plane mirror, and your reflection appears exactly as you appear, right? Or plus or minus a little bit, okay? You are the object. Your reflection, that person that you see inside the mirror, in big air quotes, right? The thing that you see inside the mirror is the image. And we found from our experiment in experiment 2 that this distance here and this distance here should be exactly the same. Again, for a flat mirror, okay? This is called the distance for the object, and this is called the distance for the image, okay? And the conclusion that you came to from that experiment was that the distance for the object will be equal to the distance for the image for a flat mirror. Okay? And that's not a trivial statement. It's a little bit weird to think about. Have you guys ever seen, what was it called? through the looking glass. It's like the Alice in Wonderland. The second part of it or whatever, if you've ever read it. She's like looking into the mirror or into that, right? And then weird stuff happens. Yeah. That's what I always think of here. But really what's happening is that the light from your face or the light from the marker or whatever it is coming in and it's bouncing off. It's converging back here, way back here at the spot where the image is. And it appears that there's another one of you back behind the mirror. And the distance between you and the mirror and the distance between your reflection in the mirror is exactly the same. Yeah?
So if you're like standing 5 feet away from the mirror, would it add on a 5 feet in the reflection so it looks like what you see would be what you would see 10 feet away?
So let me make sure that I'm understanding your question because I think I do, and I think the answer is yes, but I want to make sure I understand what you're saying. So if I'm standing here and 5 feet in front of me is the plane mirror, is that what you're saying?
Yeah.
Then my image is going to be 5 feet beyond that.
So it'll look like you're looking 10 feet away.
Right, exactly, yes. And so then if I take a step forward and I'm now 4 feet, what happens to my image? It gets closer as well, and I can keep getting closer and closer. And if you put your face really close up next to a mirror, then your image is really close up next to the mirror as well. Right? I don't know if you've ever noticed that in some restaurants and in stores, they will put mirrors up on the walls. You ever notice that?
Yeah.
Why do they do that? I mean, like for some like stores, it might be because you want to like see something, but any idea why they often will put mirrors on, like big mirrors on walls?
Does it make it look bigger?
It makes the whole space look bigger.
Illusion.
Like, that's exactly what it is. So often, especially in like small restaurants, this is where I usually think of this, like little tiny restaurants that are like in a strip mall, they can put big mirrors up and then it makes it look as though the space is a whole lot bigger. And if the little tiny room is full, then there are images of all of those people, so it looks really full too. Does that make sense? So yeah, they absolutely do use this. Yeah.
You know the hospital has like you've been inside the hospital
Mm-hmm.
and you go through like where like I don't know where it is, but they have this thing on both levels where there's like mirrors all over it and it looks gigantic.
Mm-hmm.
But it's actually like one level.
Yes.
That's what I'm thinking.
Because it's that light just keeps getting reflected off. Yeah. Yeah, that's absolutely true. Yes. Are we doing okay so far? Okay. Really quick question. This was something that was not in your lab explicitly, but I'm going to ask it. How big is the image compared to the object? What is it?
The same.
They're the same size, right? And again, not trivial, okay? So another thing that we want to write down, another observation that we can make is that the object and the image are the same size. And the technical physics term for that is that the magnification is equal to 1. We will talk a little bit about different kinds of mirrors. So flat mirrors always have a magnification equal to 1. If you ever walked around in one of those funhouse mirror areas, the hall of mirrors, where they've got the curvy mirrors, right? I always have a favorite. It's the one that makes me, not 5 feet tall, look really, really tall, right? So my image is the same distance away from the mirror as I am, but my magnification is not 1 now. Are you with me there? Yeah, it makes me look really, really tall because it's not a flat mirror, okay? We can write down these little deals. So we can say that if the image is smaller than the object, okay, the magnification is less than 1. Those are the mirrors I don't like because I'm not very tall, and so I don't want one that's going to make me look even smaller. No, thank you. If the image is the same size, then the magnification equals 1. And then my favorite ones, right? If the image is larger than the object, then the magnification is greater than 1. Now, to be clear, I don't really want to be any taller than I am. I just want to make that really clear. I have no issues with that. It's just kind of fun to pretend sometimes that you're really, really big, right? I just want to make that clear. I'm not crabby about anything. But this idea of magnification is pretty important when we're talking about different kinds of mirrors, and we'll get there in a little bit as well. All right, we're going to keep cruising unless there are questions. We doing okay? Okay, can I go ahead and scroll up? Go there. Experiment 1 told us we had an image and an object. They were the same distance. Experiment 2 basically gave us what we call the law of reflection. What was it that we did in experiment 2? You just did this. So help me out. Remind me what's going on here. I've got my mirror, and I want you to draw this in your notes too. I've got my object. And what did you do? Do you remember? It's just like 10 minutes ago.
You line the protractor up to a certain side of the mark.
Yeah, so you were looking at the object, or were you looking at the image when you lined the protractor up? You were looking at the image. So I'm going to go ahead and put the image back there. And this is not something that you did on yours, but I want you to draw this on your notes now. So remember, it's going to be the same distance back, so it's going to be back here. And so you lined up your protractor like that. You with me there? You lined your protractor up so that it was lined up with this part of the image. Okay, so this one back here, the blue one is the image. But the light doesn't actually go back there, does it? This is all in our heads. There's nothing back here. The light really came from where? Where'd the light come from? Did it come from the object? The light comes from the object. It hits the mirror and then bounces to your eye. So the light actually goes like this. So this is your eye. There's your eyeball. Okay. So that's like the observer. I've been practicing this for a few years. The light bounces off of the object, it hits the mirror, and bounces off to your eye. Okay? It tricks your mind into thinking that the light really came from back here. But it didn't, right? It actually came from here. And you measured these angles, didn't you? Because that's what I asked you to measure. So you measured this angle here, and you measured this angle here. And what did you learn? What did you find out? They were the same. Now, if I put my head in a different place, then the angle in and out are going to be different than this example. But these two angles, that pair of angles is going to match up. We call this one, you guys have seen theta before, right? We've done theta before. Theta just means angle, okay? This angle is the angle in, or the angle of incidence, okay? And this one right here is theta r for reflection. The law of reflection says, okay, that the angle of incidence, oh, let's write this down and then you can go, I promise, which is the angle in, will be equal to the angle of reflection. theta r. Okay. I do have a couple of homework questions that I put up on Canvas. They are there, and I'll put them back up here so that you can see them again if you need to. Please give them a shot. You know what? No, you just hold on to your lab. That'll be fine. You just hold on to it. It's the experience that matters the most on that one. Okay? So here are the two homework questions that I want you to work on. The second two might be a little bit challenging, but I think you can do it. So give those a shot, and we will talk. Don't worry about it. No, just hold on to it. We'll talk about them tomorrow. Have a fantastic day, you guys. Be well. Happy Tuesday.